In the year 2020, more than 13 billion miles from the Sun, a machine older than most of the engineers who now monitor it detected something that should not have been there. It was not a signal. It was not a voice. It was a number, a tiny fluctuation buried inside a stream of static. And yet that number was enough to make some of the most experienced scientists at NASA's Jet Propulsion Laboratory stop what they were doing and look again, because the empty darkness surrounding Voyager 1, our Voyager 1, was no longer behaving the way physics said it should. Space, the coldest and most vacant place humanity has ever measured, was getting denser, not by a little, not once, again and again, year after year, as if something out there was quietly rewriting the rules of the solar neighborhood, and nobody could explain why. Consider, for a moment, how strange that sentence actually is. Voyager 1 was never designed to study interstellar space. Its cameras, its spectrometers, its entire suite of scientific instruments were built in the 1970s to study planets, moons, and rings, bright and reachable targets lit by sunlight. Nobody who designed the spacecraft expected it to still be operating decades after leaving the planetary neighborhood entirely, drifting through a region of the galaxy that has no sunlight to speak of, no planets, nothing familiar at all. And yet here it is, an accidental interstellar probe, forced by circumstance and sheer longevity into becoming humanity's only direct witness to a part of the universe it was never built to explore. Every reading it sends back is, in a sense, a bonus, squeezed out of hardware that has already outlived its purpose by nearly half a century. That a machine operating so far past its intended lifespan is the one delivering data serious enough to challenge established models of interstellar space says something about both the resilience of 1970s engineering and the sheer scarcity of alternatives. There is no backup Voyager. There is no second chance to build this kind of long-duration in situ observatory before the current one falls silent for good. This is the story of that mystery and of the two aging spacecraft still fighting to send it home. To understand why a change in plasma density could shake the foundations of heliophysics, you first have to understand what Voyager 1 and Voyager 2 actually are, and why nothing built since has come close to replacing them. Launched in the late summer of 1977, just weeks apart, the twin probes were designed for a mission that was supposed to last 4 years. Their job was simple on paper: fly past Jupiter and Saturn, photograph the giant planets and their moons, and then, if the hardware survived, perhaps continue outward. Nobody who worked on that launch pad in Florida seriously expected the spacecraft to still be transmitting data in the 2020s. And yet, decade after decade, Voyager kept going. It photographed the volcanoes of Io. It captured the storms of Neptune in cobalt blue. It became the first human-made object to leave the solar system's protective bubble and enter the space between the stars. Nothing else we have ever built has traveled so far, or lasted so long, in a place this hostile. That protective bubble is called the Heliosphere, and it is worth pausing on what it actually does, because everything about this mystery hinges on the boundary at its edge. The sun does not just emit light. It emits a constant outward wind of charged particles, plasma streaming in every direction at hundreds of kilometers per second, inflating a vast bubble around the entire solar system. Inside that bubble, the environment is shaped by the sun. Radiation levels, magnetic fields, particle density, all of it answers to our star. But that wind cannot blow forever. Eventually it runs out of pressure, pushing against the thin gas and magnetic fields drifting between star systems. The leftover material from exploded stars that lived and died long before our sun ever ignited. The point where the solar wind finally loses that fight is called the heliopause, and it marks the true edge of the solar system, not in the sense of planets, but in the sense of the sun's authority over the space around it. Voyager 1 crossed that invisible frontier in August of 2012, and Voyager 2 followed in November of 2018. For the first time in history, humanity had instruments physically present in interstellar space, sampling the material between the stars rather than guessing about it from Earth. And almost immediately, the data coming back did not match the models. Scientists had predicted that crossing the heliopause would cause a sharp jump in plasma density, since interstellar space was expected to be significantly denser than the diluted wind inside the heliosphere. That part checked out. What nobody predicted was what would happen next. The density did not simply jump once and stabilize. It kept climbing and climbing. Year after year, the deeper Voyager traveled into interstellar space, the thicker the plasma around it became, far beyond what any existing model of the local interstellar medium had forecast. At first, researchers assumed this was a temporary disturbance, some kind of pressure wave rippling outward from the sun, compressing the interstellar gas the way a shock wave compresses air. The sun does produce these disturbances. Coronal mass ejections, enormous eruptions of solar material, can travel for months or even years before slamming into the heliopause from the inside, sending ripples through the boundary and into the space beyond it. In 2012, and again in 2013, Voyager 1's plasma wave instrument picked up exactly this kind of event, a burst of oscillations that let scientists calculate the surrounding electron density directly, using the same physics that lets you estimate a stadium crowd's size from the pitch of their combined roar. The density measured in 2013 was already surprisingly high, but it was explainable. A shock wave had passed through, compressed the plasma, and the readings would presumably fall back toward baseline once the wave moved on. It never did. By 2014, then 2015, then into the back half of the decade, the density readings kept coming back elevated. Every time researchers expected the numbers to settle down into a predictable gradient, the interstellar medium refused to cooperate. Then, in 2020, something happened that turned a puzzling trend into an outright anomaly. Voyager 1's magnetometer, the instrument responsible for measuring the strength and direction of surrounding magnetic fields, registered an abrupt and significant jump in intensity. At almost exactly the same time, the plasma density spiked again, this time even higher than before. Researchers had seen transient jumps like this in the past, brief disturbances that faded back to normal within months. This one did not fade. The elevated readings held, and kept holding month after month, long past the point where any known shock wave should have dissipated. That persistence is what changed the conversation inside NASA's heliophysics teams from curiosity to genuine concern. If a temporary pressure front were responsible, the numbers should have relaxed back toward the pre-2020 baseline once the disturbance passed through and continued outward, the way ripples fade after a stone is thrown into a pond. Instead, by the time researchers published updated measurements, extending Voyager 1's density readings out past 160 astronomical units from the Sun, the density had settled at a value nearly triple what had been recorded when the spacecraft first crossed into interstellar space back in 2012. Something out there was not behaving like a passing wave. It was behaving like a standing feature, a structure, a region of space that was simply persistently denser than anything the models of the local interstellar medium had prepared scientists to find. Which raises the obvious question that has occupied plasma physicists for the better part of 5 years now. What exactly is Voyager flying through? There is no single accepted answer, and that uncertainty is precisely what makes this such an unusual moment in space science. Several competing explanations have been proposed, each accounting for part of the picture while leaving other pieces stubbornly unresolved. One leading idea treats the density increase as evidence of compression at the edge of the heliosphere itself, a kind of cosmic traffic jam. As the solar wind pushes outward and interstellar material pushes inward, the two can pile up against each other near the boundary, like snow accumulating in front of a plow. If Voyager is sampling material caught in that compression zone, the elevated density could reflect local crowding rather than a genuine change in the broader interstellar medium. It is a tidy explanation, and it fits some of the data, but it struggles to explain why the density has remained so stable for so long, well beyond the timescale over which a compression front driven by solar activity should be expected to ease. A second explanation looks outward rather than inward, toward the enormous structure known as the local interstellar cloud. The vast region of gas the entire solar system happens to be drifting through at this moment in galactic history. Some researchers have proposed that Voyager may be approaching, or already crossing, the outer edge of this cloud, entering a genuinely different pocket of interstellar material with its own distinct density and magnetic characteristics. If true, this would mean the spacecraft is not measuring a temporary disturbance at all, but rather documenting a real, permanent transition in the structure of the galaxy immediately surrounding our Sun. Information that no ground-based telescope or Earth-orbiting instrument could ever gather, because you cannot measure the texture of interstellar plasma from millions of miles away. You have to be inside it. A third possibility, less discussed publicly but taken seriously within the research community, involves the magnetic field data itself. The intensity of the magnetic field Voyager is now recording is higher than pre-launch models anticipated for this region, and its behavior does not cleanly separate from the density anomaly. Some scientists suspect the two phenomena are linked, that whatever is compressing or restructuring the plasma is simultaneously reshaping the magnetic architecture of local interstellar space, a process that could ripple outward and eventually affect how cosmic radiation reaches the inner solar system, including Earth. The heliosphere is not just a curiosity. It is a shield, deflecting more than 70% of galactic cosmic radiation away from the planets that orbit within it. Any structural change happening at its outer boundary is not purely academic. It touches the radiation environment every future deep space mission and every future astronaut will have to contend with. None of these three explanations has been confirmed. None has been ruled out. And that, more than any single number, is what makes this genuinely rare in modern astrophysics. Most of what reaches the public as a space mystery collapses quickly under scrutiny, explained within weeks by a known phenomenon, or dismissed as instrument error. This one has not collapsed. It has been sitting in front of some of the most qualified scientists on the planet for half a decade, and it is still standing. Complicating the investigation further is the fact that Voyager itself is dying, and every year makes the remaining data harder to gather. Both spacecraft are powered by radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium into electricity. That decay is constant and irreversible, which means the power available on board has been shrinking steadily since the day of launch, and there is no way to refuel it, no way to service it, no way to send a repair crew across 15 billion miles of empty space. To keep the spacecraft alive for as long as possible, engineers at NASA have spent years selectively shutting down individual instruments, sacrificing entire fields of data collection to preserve enough power to keep the remaining instruments and the radio transmitter itself functioning. The plasma science instrument, the very system responsible for some of the density readings driving this mystery, has already been powered down on parts of the mission to conserve energy, forcing scientists to rely increasingly on indirect methods, like the plasma wave instrument's ability to infer density from oscillation frequency rather than direct measurement. The fragility of the mission became starkly clear in November of 2023, when Voyager 1 suddenly began transmitting garbled, unreadable data back to Earth. For months, engineers could not determine what the spacecraft was even trying to say. The eventual diagnosis, delivered after painstaking work sifting through code written for a computer system with a fraction of the processing power of a modern calculator, traced the fault to a single corrupted chip inside the flight data subsystem, a component that had likely either degraded after decades of use or been struck by a high-energy cosmic ray. An ironic possibility, given that Voyager spends its days swimming through exactly the kind of radiation environment that could cause such damage. Engineers eventually worked around the failure by relocating the affected code elsewhere in the spacecraft's limited memory, coaxing readable data back out of a machine that, by any reasonable standard, should have gone silent decades ago. But the data collected during the months of the outage was lost permanently, a blind spot in the record precisely during a period when scientists most wanted continuous density measurements. That near loss underscored something the entire Voyager team has understood for years, but rarely says aloud. The window to solve this mystery using Voyager's own instruments is closing, and it is closing on a fixed and unforgiving timeline. Current projections put the point at which the spacecraft's dwindling power supply can no longer sustain any functioning instruments sometime in the back half of this decade, a deadline that has already forced difficult decisions about which systems to sacrifice first. When that day arrives, the spacecraft will not explode or shatter. It will simply go quiet, drifting onward at more than 38,000 miles per hour, carrying its golden record and its aging instruments into a silence it will never break again, a ghost ship continuing outward on a trajectory that, in roughly 40,000 years, will bring it within less than 2 light years of an obscure star in the constellation Ursa Minor. But by then, it will have been mute for tens of thousands of years, its transmitters as dead as the batteries that once powered them, which is precisely why every scrap of data still coming back from both spacecraft is treated with an urgency that borders on reverence inside the halls of JPL. Every reading of density, every fluctuation in the magnetic field, every faint whistle picked up by the plasma wave instrument is one of a finite and shrinking number of glimpses humanity will ever get of this region of space, gathered by hardware that cannot be replicated with current technology on any realistic timeline. There is no mission currently funded or even seriously proposed that could reach interstellar space and begin returning comparable data before the second half of this century, even using the fastest propulsion concepts under study today. If Voyager falls silent before this density mystery is resolved, it may remain unresolved for the rest of most of our lifetimes, an open question hanging over the edge of our solar system with no way to close it. That reality has changed how scientists talk about the readings that are still coming in. What might have been treated as a routine anomaly in a healthier, better-funded field of research has instead become one of the most carefully scrutinized datasets in modern heliophysics, cross-checked against magnetic field readings, checked against models of solar activity, checked against everything the sun was doing at the time. Each disturbance was recorded in an effort to rule out mundane explanations before anyone allows themselves to consider stranger ones. And so far, the mundane explanations keep falling short. The compression models explain part of the pattern, but not its persistence. The interstellar cloud boundary theory explains the possibility of a structural transition, but does not yet have independent confirmation from any other instrument or mission. The magnetic field coupling theory raises more questions than it answers about what precisely is doing the reshaping. What makes this particular unresolved question feel different from the usual parade of speculative space headlines is the credibility of who is asking it. This is not a fringe claim circulating on social media. It comes from peer-reviewed papers published in journals, including Nature Astronomy and the Astrophysical Journal, authored by researchers who have spent entire careers studying this single spacecraft and its instruments, people who understand better than almost anyone alive exactly how skeptical to be of an anomalous reading before treating it as real. When scientists of that caliber openly state, on the record, that the density trend defies existing models and that they genuinely do not know what will happen next, it carries a different kind of weight than a headline promising the secrets of the universe. There is also a quieter, more unsettling dimension to this story, one that rarely makes it into the more sensational retellings. The interstellar medium Voyager is now sampling as not empty space in any meaningful sense. It is the recycled material of dead stars, gas and dust enriched by generations of stellar explosions long before the sun existed, drifting through the galaxy in slow, vast currents, shaped by forces far larger than our solar system. Every density reading Voyager sends home is, in a very real sense, a measurement of galactic history, a fingerprint of processes that occurred millions of years before humans existed to wonder about them. If the region surrounding our solar system truly is transitioning into a different, denser pocket of that ancient material, it would mean the environment around Earth itself, protected as it is by the Heliosphere, is entering a genuinely new chapter, one that could subtly influence the radiation reaching the inner solar system for centuries or millennia to come. That is not the language of a monster in the dark. It is something arguably more profound. Proof that our solar system is not a fixed, unchanging bubble, but a structure still drifting through and reacting to the wider architecture of the galaxy. It is worth remembering, too, that Voyager was never sent out purely as a scientific instrument. Bolted to the side of each spacecraft is a golden phonograph record, etched with sounds and images meant to represent life on Earth. Greetings recorded in dozens of languages, music spanning cultures and centuries, a message assembled under the assumption that someone, someday, somewhere, might find it drifting through the dark. That symbolic gesture, made in the 1970s with almost no expectation it would ever be tested, has quietly become one of the more poignant footnotes to this entire story. The spacecraft carrying humanity's introduction to the galaxy is the very same spacecraft now delivering evidence that the immediate galactic neighborhood beyond our sun is stranger, denser, and less understood than anyone who recorded those greetings could have imagined. Voyager was sent out to say hello. It has ended up teaching us that we barely understand the room we are standing in before we even reach the door. It is also worth being clear about what this mystery is not, if only because so much of what circulates online about Voyager leans toward the sensational. There is no verified evidence of an artificial signal, no confirmed detection of intelligent communication, and no credible indication that anything with intent is responsible for the density changes being recorded. Extraordinary claims along those lines that occasionally surface in less rigorous corners of the internet do not originate from NASA, from JPL, or from the peer-reviewed literature actually describing this phenomenon. The real mystery does not need embellishment to be compelling. A region of space behaving in a way that contradicts decades of accepted physics, recorded by the only instruments ever to sample it directly, is remarkable enough entirely on its own merits, without inventing a narrative the data does not support. If anything, the restraint shown by the scientists involved, their refusal to leap toward the dramatic explanation when a mundane one might still be waiting to be found, is part of what makes their genuine uncertainty so credible. For now, the honest answer to what is happening in the space around Voyager 1 is that nobody fully knows. The leading researchers studying the data have been careful, publicly and repeatedly, not to overstate their confidence in any single explanation. What they will say, on the record, is that the density has climbed far beyond pre-crossing predictions, that it has remained elevated for years rather than months, that the magnetic field data appears connected to whatever is driving the change, and that no existing model of the local interstellar medium fully accounts for what two nearly 50-year-old spacecraft are still, against every reasonable expectation, managing to send home. Whether the coming years reveal a mundane cause, some slow-moving pressure front finally easing back toward baseline, or something closer to a genuine restructuring of the space immediately surrounding our solar system, one fact remains constant. Two machines built with less computing power than a modern pocket calculator, launched before most of the scientists now studying their data were even born, are still out there, still listening, still reporting back from a region of the galaxy no other instrument has ever touched. Every signal that reaches Earth takes more than 22 hours to arrive. A whisper crossing 15 billion miles of the coldest and quietest place science has ever measured. And for as long as that whisper keeps coming, the question of what exactly Voyager has found out there in the dark remains one of the very last true mysteries the edge of our solar system still has left to give us.